So I wanted to quickly follow up on the loops demo I gave previously and just kind of point out a couple more of the features that I think are interesting about these. The first thing is that you can create the loops with natural language here. As you can see, I'm just in the platform agent, and I've just got a prompt here kind of describing what I want, which is the name of the loop, my budget settings, and then I just describe each of the nodes I want. There's a gather node, there's a translate node. This is for translating the posts into French, and then a save. And then I kind of describe how they should connect here, if it's not already obvious in the descriptions. So we'll just hit this, see if it will generate the loop as I have described it. Okay, so now that's done, we should be able to go back into our workflows. And so this was a previous one I ran, but this is the current one, org-wide. And so we'll see, yeah. So it's got my prompts right. It looks like it's actually got the for each correct as well. So yeah, it looks good. So, if you were kind of like not sure how to wire it up based on like what I described in the last video and the logic and all that, just feel free to have the agent itself create the loop for you. So now that we have this built, the things I really wanted to show you guys are a few optimizations we've included to really reduce pretty greatly the number of tokens you'll spend on these loops and elsewhere in the app, like chatbots and stuff like that. Pretty much anywhere you would invoke an agent benefits from these solutions that basically revolve around certain cache types, and they kind of take the shape of like memoization, even though it's not that in the traditional sense. So one of the ideas we borrowed from this project, which is really cool, called the $0.10 agent memory. So it uses something called symbolic memory. And, we use Postgres in our containers, and, SQLite for us is on the distributed apps. Like if you have a mobile app or something like that, with our sync library, those get SQLite. But where this would be running is Postgres, so there's just some differences. We just took the core idea and adapted it to oalo. And then the other one is this called Graphify. Again, we don't use either of these directly. We just sort of borrowed the idea, implemented in oalo where we knew we could use it to save tokens. So let's go ahead and run this, and I'll explain a little more about it as it goes. So the reason this works really well is the fact that this DAG is recursive. That means that it's not in a persistent session. Each node spins up its own agent and sort of restarts, in this case, the Claude code session, meaning that we can take advantage of Anthropic's cache, which happens when the byte prefix matches what's already been called. So that means like the system prompt, the tool definitions, the baked in context, the instructions that we give it. It doesn't include what comes after that, which is like the control boundary, which is the, hey, translate this post. Each post is different because of for each, right? But the actual setup and the calls and everything like that are the same. And that's because we use recursive session and not a persistent session. So the next one hits it, whereas if it were persistent, it would just continue building, and that you wouldn't get the cache. And if you hit the cache, this is important, you reduce your cost by 90%. All right, so if you can engineer cache hits through the loop, you save 90% on tokens. And we also have kind of a trick where we remove some of the stuff that would be variable in that, let's call it like header context that gets cached, and we move it from the system prompt into the user session. Stuff like on vars and like get state and commands and stuff like that. So with this architecture, we can just make sure that after the first node, everything subsequently gets hit with the cache. And that's thanks to Anthropic and just a little bit engineering here. But what makes it really work is because of the symbolic memory. That acts as the ability for this recursive engine to have continuity. And what that does is when the symbolic memory is cached, it kind of like writes a log to it. Basically, like the decisions that it made in a previous node, summarizes, puts in a post-it kind of, you can think of it, and then it passes it to the next node. And instead of having to recollect all that context, it can see, hey, this is what the last one did. The kind of decisions it made, like for translating to French, you'll see it's consistent across what word it used for you. Is it tu or is it vous? Because it could look at the previous invocation because of the symbolic memory, because of the post-it note, and make sure everything is consistent. And that comes in handy when you need that reflection or those looping to kind of refine the data that we talked about. And that also saves a ton of tokens because it doesn't have to figure all that out again, right? So those two things combined make this recursive option great. And this is kind of the direction things are heading in the industry with like the recursive language model push and stuff like that. So that's basically what this is. And this is just an optimization around that. You'll see here in the history, after you get through a run of the loop, now it will show you exactly how much you save per turn and in total with the cache hits, right? So you'll see here, far and away, the most tokens are cache read, which is great because you save on all of that. And you'll see here kind of per turn. You'll see also what the symbolic memory passes to keep that continuity intact, even though we're using the recursive method. That's kind of that post-it note I described earlier. And you'll see, per turn, the amount of fresh tokens versus how much are being reused and cached is like amazing. This is a translation, right? This is Opus running, and this was like 4 cents, right? So this technique really does help cut down on the cost for this stuff. So I just kind of wanted to go over, just the amount so you can visualize, how much you're saving with this, and show you that, you can achieve that persistence that you would normally have in like one session with the symbolic memory injected per node. You can see exactly what it's doing here, but still use the recursive approach for the loop, which is kind of the direction the industry is going with, like the recursive language models and everything like that. It's pretty much recognized now this is the way to cut down on costs and make this sort of computation, viable. So okay, so just to kind of show where the graph cache will help save you on tokens, I created a slightly more complicated instance here, just with more relationships and everything, because the savings here really compound the larger and more the larger your system, your distributed system grows. So the more relationships and stuff like that, and if you have even just a few apps with multiple relationships, it's the same scenario as if you have a bunch of apps here I generated with a few relationships, right? So if we come in here just real quick. So I'm just instructing it to do something that would require for it to do some walks and some greps. And I'm explicitly saying, don't use the graph, use the greps here. So for each app in the org, give me a per app breakdown listing every data table the app uses. And then I tell it to kind of go into that further so that it needs to do a bit of walking. So I generated quite a few, so I'll have to do a bit of work here. Probably speed this up. All right, so here we have a response. Here are the numbers for that one, right? So we'll make note of that. And I'm just gonna run it again. But first I'm gonna kind of clear this out just to make sure nothing gets reused in the cache. To just make sure the example is good, so just bear with me 1 second. All right, so come back in, fresh slate, and we'll run it with the graph, which it will automatically use if you don't instruct it otherwise. Or if it, if it uses the graph and can't get the answers it needs, it'll start walking. But all right, so you'll see here, these are the numbers with the graph. So anyway, hopefully that's a decent demonstration of where the graph caching comes in handy, not just for you to see how everything relates to one another, but also for the LLM, so it doesn't have to do excessive research costing you tokens, right? So again, we're trying to save you as many tokens as possible. We're not trying to milk you for tokens or anything like that. We want your most efficient agentic routines and loops to be here on Oalo. And we want we're always searching for ways to optimize it. We have our eye on all this really interesting stuff coming out in the open source community and elsewhere, and research and whatnot to try to see how we can fit it into the platform to save you on token costs. So if you want all that baked in without having to worry about it yourself, consider oalo.ai for your next project. So thank you for watching.